I will share my contact details shortly now. I will be joined by Mr. Rajesh Soman. He's the Director of Integra Technologies. And Integra Technologies is our premier business partner of Red Hat. They will be presenting on OpenShift today. It will be more of a technical presentation. Yes, please keep asking your questions. We will keep making a note of your questions and definitely we will answer them.
Good morning.
Welcome everyone. I hope you guys can hear me.
Yes,
So once again, welcome everyone. Thank you so much for joining me on this webinar on Red Hat OpenShift. This is basically an introduction to the Red Hat OpenShift container platform. This is basically targeted toward people who have some knowledge of container and or containerization. What is it? And they have some knowledge about containerization, and they are looking into a advanced platform to manage their container and their container orchestration tools. But before we begin, a little bit about myself. My name is Hazik Naeem, and I am a solution architect at Integra Technologies. A brief intro about Integra. We were founded in 2006 as an enterprise open source solution provider. Today, we are a Red Hat premium partner and a Red Hat and an AWS commercial and public sector partner for this region. We support all Linux apart from the enterprise ecosystem that runs on those operating system, MySQL, Cassandra, Nginx, and Apache. We also support Microsoft technologies. We have a fully certified team of Linux, AWS, and Microsoft engineers. Our team is completely based in Dubai, and we are providing the entire life cycle. We provide consultancy, implementation, support, and provide services. Our customer list include enterprises in many vectors. It includes retail, construction, fintech, customer service, and university, and many more. We are also very strongly present in the financial sector as well. And now let's get into the topic of the webinar. But before we start our discussion on the Red Hat OpenShift container platform, I want to talk a little bit about I'm crossing my finger and hoping that this time our connection doesn't break. And we'll continue from the beginning of the slide. So like I was talking about the container orchestration. So it's about managing the life cycle of containers. Traditionally, we had an administrator who used to manage these bare metal servers. But in the world of containerization, it becomes impossible when you have thousands of containers spawning across hundreds of container nodes for an administrator to manually manage those nodes. So basically, a container orchestration tool is essentially responsible for provisioning and deployment of these containers across the cluster. It is responsible for availability of container nodes. The container orchestration tool is also responsible for scaling up the application by adding more containers when there's a load spike, and scaling down the application by removing the container when the load decreases. It is also responsible for publishing the endpoint of the cluster and providing load balancing for these applications. There are a lot of container orchestration tools that are available in the market. We can spend a whole day just talking about those, but here are some of the most common ones. There's Apache Mesos, which is slightly older than Kubernetes. And it is completely open source and is currently being managed by the Apache Foundation. Next, we have Docker Swarm. So Docker Swarm is always quite easy and simple to use, but it's not really designed for a complex workload or for an enterprise workload. Finally, we have Kubernetes. Kubernetes originated from the Google's Borg project, and it has become the golden standard for container orchestration tools. Now, a lot of different offerings of Kubernetes are available in the market, including Amazon's EKS, which is Elastic Kubernetes Service. We also have Google Cloud's Kubernetes engine. There is also the Azure Kubernetes engine as well. All of these are open source offering of Kubernetes. But in order to build a complete platform, one has to include the vendor-specific tools. For example, in case of EKS, if you want to build a CI/CD pipeline, you will have to integrate code pipeline, code build, and the whole code ecosystem. Similarly, if you want to monitor your cluster, you will have to integrate with CloudWatch. Introducing Red Hat OpenShift Container Platform. OpenShift is an enterprise-ready Kubernetes. Basically, what that means is that OpenShift has all the features ready and built to support enterprise customer, which normally have unique requirements such as single sign-on, role-based access control. These enterprise have requirements like auditing, logging, and monitoring. OpenShift Container Platform is actually a complete hybrid platform. It provides out-of-box services such as CI/CD pipeline, monitoring and logging tools, a built-in registry service, software-defined networking, and software-defined storage. All of these solutions are built on top of open source solution so that there is no vendor locking. The Red Hat OpenShift Container Platform can run on practically any public or private cloud. It can also run on bare metal servers, which means that you can run them on your data centers, inside your data centers. There are a couple of other offerings from Red Hat OpenShift. There is the Red Hat OpenShift Dedicated and Online, which is basically a managed service for Red Hat OpenShift, where certain aspects are controlled and managed by Red Hat, and the user is provided certain controls. We also have Red Hat OpenShift code-ready containers. This is basically a minimized version of Red Hat OpenShift, sometimes also known as Minishift. This is designed to run on developers' laptops so that they can get a user environment before they can go into production. Apart from running a self-managed cluster of Red Hat OpenShift Container Platform, you can also run a fully managed OpenShift cluster on Azure and IBM. In the third quarter of this year, we are expecting the launch of Amazon Red Hat OpenShift service. With this launch, you can run Red Hat OpenShift cluster inside your AWS account as a fully managed service. And you can integrate your OpenShift cluster with more than 170 plus already available AWS services. Now let's talk a little bit about some of the Red Hat OpenShift features and components. So OpenShift uses Kubernetes as its container orchestration engine, which is designed for high availability. OpenShift uses Kubernetes to deploy internal components as well as user applications. Red Hat OpenShift Container Platform uses a very lightweight operating system, which is optimized for running containers, and all the necessary packages are pre-installed. OpenShift provides internal and external load balancing. OpenShift can even integrate with external cloud provider load balancers. Basically, the internal load balancer is built out of HA proxy, and external can depend on the cloud provider that you're using. OpenShift can provide auto-scaling and self-healing for user applications as well as self-applications, for internal applications. Auto-scaling can even scale the worker nodes that are running user applications. Red Hat OpenShift comes with advanced application monitoring solution using Prometheus, which provides hundreds of matrices from both the application as well as the cluster. The OpenShift also ships with the ELK stack for logging and analysis. And there is also the Grafana dashboard with pre-built dashboard that you can use. An internal DNS server using the OpenShift, using the open source and lightweight core DNS is also provided, and all applications are given access to this internal DNS for name resolution. This allows applications to communicate with each other regardless of their continuously changing IPs. This makes service discovery quite easy and seamless. You can also integrate third-party service discovery solution if you need. A Red Hat OpenShift container platform provides developers and DevOps engineers the ability to automate the development and deployment of their application. It basically provides the S2I feature, which is basically a source to image tool. It takes your source repository and converts that into an image and stores that into an internal registry service. The developer catalog is a place where you can publish and access application templates. It supports many runtimes such as Python, Ruby, Java, Node.js, and also databases and many messaging services as well. You can extend the catalog by installing custom or new runtimes. You can extend the OpenShift API using operators. An operator is a method of packaging, deploying, and managing a Kubernetes native application. As discussed earlier, Red Hat OpenShift Container Platform uses Kubernetes as its container orchestration engine. Red Hat OpenShift Container Platform uses Red Hat Enterprise Linux Core OS. Core OS is basically a lightweight container optimized operating system. Core OS is immutable operating system, which means that runtime changes are not applied to the operating system. This immutability allows OpenShift worker and master nodes to be added seamlessly, and they are updated seamlessly. This also means that there is no need for system administrator to manage these nodes. Cryo is now the default runtime engine. Docker is now deprecated. Cryo is fast and lightweight container engine designed and optimized for Kubernetes. Cryo is also OCI compliant. Red Hat OpenShift Container Platform ships with pre-installed and configured cluster administration and management tools such as the Web Console. It also comes with an internal registry service to store your images, container images. It also comes with a logging and monitoring solution and a complete CI/CD platform. Red Hat OpenShift Container Platform provides software-defined networking and software-defined storage, which abstracts away the control plane from the underlying storage and networking vendors. Red Hat OpenShift works in a master and worker architecture. What that means is that we have dedicated nodes for worker components and dedicated nodes to run user applications. The master nodes run Kubernetes container orchestration components such as the API service, the etcd data store, which stores the state of our applications. The controller and scheduler, which monitors the state of our application and nodes and ensure that containers are running on the correct node. Then we have the worker node, which runs user application. This worker node basically communicates back to our master node. We also have something called the infra nodes that runs OpenShift supporting components such as the registry service, the monitoring and logging service, and the network and storage components. Now there is a major difference between Red Hat OpenShift Container Platform 4 and its predecessors, and that is the RHEL Core OS. OpenShift 4 forces you to use Core OS as its underlying platform. Previously, this was optional. You can still run your worker nodes as Red Hat Enterprise Linux servers, but master must run on Core OS. Let's take a closer look at the cluster worker and look at what it looks from the inside. The master node. Basically, the master node has two systemd services running. We have the Cryo container engine, which runs the container engines, which runs the containers. And then we have the kubelet agent running as the systemd service. Now, kubelet agent ensures communication between the master components and the container engine runtime. On top of that, we have Kubernetes services such as the API service, the etcd data store, controller, and scheduler. On top of those, we have OpenShift services such as the core DNS, the OpenShift controller, and there are many other services as well, which are not mentioned here. And we also have a very important component called the OpenShift API service. Normally, a user communicates to this API service and it authenticates against the OpenShift OAuth operator that is installed. Normally, a user will not communicate directly to the API service, the Kubernetes API service. It will create the connection to the OpenShift API service, and the connection or a request could be proxied back. And now let's take a look at the worker node. Worker node look similar to the master nodes. We have the two systemd services running, the Cryo engine, the kubelet agent, and plus we have a proxy service. This proxy service ensures that the communication between other nodes running the same pods in a different machine could be communicated. On top of that, everything would be the user application that is running in containers. An example OpenShift container platform architecture could look something like this. We can modify this, but an example could be something like this. We have the control plane and the worker node running our control plane, and worker node running our user applications. Then we will have the infrastructure nodes running the logging and monitoring service and the routing, and including this will also include the registry service as well. Plus, we will require an external load balancer. This load balancer is required to publish our user application. This could be a hardware load balancer or a cloud provider application. Now, let's talk a little bit about some of the core concepts of Kubernetes or OpenShift. At a basic level, we have pods. Pods are basically an atomic unit. These are the smallest unit that runs inside your cluster. Pod is basically one or more container running inside an isolated namespace. These containers would share the IP, will also share the port range. They will also share resources such as CPU, memory, and disk. Next, we have services. Now, for a single application, there might be multiple pods running at the same time. In order to handle the load for that particular application, services are introduced. These services load balances our load back to our replica pods. It identifies its pods using something called labels. Now, labels are key value pair which are attached to our pods and containers, and services identify that using that label. We also have the registry service. Registry is basically a place to store your built images. Normally, you would require a build service to build your source into an image and then store it inside a registry. Container or pods would be running based on the location of your registry or your image location. Registry is also capable of versioning these images. Another important component is a user. A user is something that interacts with the OpenShift API. It is granted permission using something called roles. Next, we have namespaces and projects. Now, namespaces is an isolated namespace, and basically namespace is a Kubernetes construct, while project is an OpenShift construct. OpenShift takes that namespace idea and applies some additional annotations on top of namespaces and calls itself projects. Normally, you don't directly create namespaces in OpenShift. You create projects, and namespaces are automatically created at the backend. The project manages your namespaces in a way. A replica controller ensures that a specific number of pod replicas are running at all time. This means that if there are too many pods, the replica controller will terminate the extra pods, and if there are too few pods, the replica controller starts more pods. Remember, pod is basically a collection of containers, or could be a single container. Next, we have replica set. So the idea of replica set is much similar to a replica controller. It ensures a certain number of replicas of a pod is continuously running at all time and ensures capacity. But it does that based on a selector, which is a matching-based selector. If we look at the previous replica controller definition, the selector here is a single value pair, while in the replica set, we have a matching expression that we can define. That's the only advantage of using replica sets over replica controller. Similarly to replica sets, we have daemon sets. Now, daemon set ensure that a copy of a single pod is running on all the nodes, or at least the specified node at all time. The use cases for daemon sets could be running a monitoring service on your nodes, or running a log collection application on your cluster. You can run daemon sets both at worker nodes as well as master nodes. Finally, we have deployments. You normally don't write replica sets yourself, or you don't create pod definition directly. You deploy them. Ideally, you would deploy them through something called deployments. Now, deployment creates that replica set, which creates the pods. It has the capability to add lifecycle hook. We can create deployment strategies. We can even do auto scaling with these kind of deployments. While it was a little different in scaling replica controllers or replica sets. If you look at the definition, we only define the template, which defines the container pod definition, and we have the kind type, which defines the deployment. Next, we also have machine sets. A machine is basically a fundamental unit that defines a node. For example, in AWS, we can define something like m5.large as a single unit, or a type of a VM as a single machine, and that machine would be considered as a single type of machine. Now, we also have machine set. Machine sets are what machine set does to machines what basically replica sets does to pods. It ensures a certain number of replica machines are running at all time. You can set the minimum and maximum scaling boundary of a node in a specific machine set, and machine auto scaling maintains that range of nodes. You can set a cluster-wide scaling limit for resources such as CPU, cores, node, memory, GPU, and so on, with cluster auto scaling. Finally, we also have machine health checks. A machine health check resource detects when a machine is unhealthy, deletes it when a machine becomes unhealthy. Now, machine health checks are supported on certain platforms. Not all of them, or not all platforms are supported with machine health checks. And so now building from our knowledge from the previous section, in this section, we will talk about operators. An operator is a method of packaging, deploying, and managing Kubernetes native application. A Kubernetes native application is an application that is both deployed on Kubernetes and managed using Kubernetes API, or some tool like kubectl or OC. Advanced operators are designed to handle upgrades seamlessly, react to failures automatically. Basically, operator contains the operational knowledge of a stateful application that they are deploying. It converts the management of an application into code, and this eliminates human error from the application. They are not only used to set up and deploy stateful application, but also to set up and manage the OpenShift cluster itself. Such operators are known as cluster operators. Now let's take an example. Imagine that there is an application that is being deployed, that is a stateful application and is being deployed in OpenShift or Kubernetes. Once that application is deployed, it will be the job of operators and administrators to manually manage it, whether it is updating the application or patching or taking backups or scaling the application. That is all handled by the administrators and application operators. What if we take that operational knowledge and convert that into code? This is the idea behind operators. Operator will have codified all the operational knowledge, for example, updating, patching, taking the backups, or scaling the application, and made it available to the application automatically. Operators are built on the Kubernetes concept of resources and controllers. We have already discussed some of these resources and controllers previously. So a resource could be something like a pod, a service, or a route, while controllers, which are also known as resource controllers, they are responsible for managing these resources. For example, we have seen deployments can create pods and manage and update those pods and ensure the life cycle of a pod. Kubernetes operators are also built on the same concept. So for example, if I run something like OC get pod or deployment or replica set, OpenShift API would understand these resources and controllers. But let's say if I wanted to create my own kind of resource in OpenShift or Kubernetes and want Kubernetes to understand them, for example, if I run OC get custom service, the OpenShift API will not understand what that is. How can I make Kubernetes API understand my custom resource? This is the idea behind custom resource definition. This is actually achieved by writing a custom resource definition, which defines the API calls that needs to be understood by the Kubernetes API in order to respond. Based on these custom resource definition, we create custom resources. Now we have created this custom resource. Using our custom resource definition, we have created this custom resource. Now we need to create a custom controller to manage this new custom resource. This is exactly what an operator is. Operators are essentially custom resources, custom resource controllers. This new operator will monitor our custom resources, and based on the operational knowledge that the operator have, will manage, deploy, and publish the URL and ensure the scalability of this application. Now, how do we write these custom resources or custom controllers or operators? This is done using the operator framework. Operator framework is an open source tool for building, testing, and packaging operators. The operator framework makes these tasks easier than coding directly to the low-level Kubernetes API by providing something like the Open Operator software-defined kit. The operator SDK is basically Go libraries that are available to you, and you can use them to build custom operators. Technically, you don't need the SDK as well. You can write your operators in any programming language that you prefer. You can even write them in Ansible if you want. Operator SDKs basically makes your life a little bit easier by introducing pre-built libraries. We also have Operator Lifecycle Manager. The Operator Lifecycle Manager helps user install, update, and manage the lifecycle of operator and their associated services running on the cluster. Operator Lifecycle Manager itself is an operator. Then we have Operator Registry. This is where Red Hat certified operators are installed and available to you in the OpenShift cluster platform. We also have Operator Hub. This is a place where you will find community-written operators. You can go to operatorhub.io and download and utilize them, or upload your own operator if you have a custom application that you want to build. Finally, we have operator metering. The idea behind this is to report back matrices to the operator creator so that they can get an understanding about how operator is performing in a certain workload. We also have the operator maturity level. The Helm SDK can be used to basically do a basic installation of an operator or a Kubernetes application. But with operators, you can go as far as building a seamless upgrade, creating the whole full life cycle, even build deep inside, or make it fully autopilot where application automatically scales vertically and even horizontally. It will automatically detect anomalies and schedule tuning for itself. All of this could be written in Ansible, Go, or any other programming language that you want. In this section, we'll talk a little bit about OpenShift authentication, networking, and storage. Basically, we have a user. I think we have discussed user before, but user is basically an API service. It is assigned permission using roles, and it basically communicates to the OpenShift API endpoints. Next, we have identity. Identity is basically a shadow resource. It stores the data of a user. It stores the authentication information about a user. Each user resource is associated with a single identity resource. We also have service account, which are also actually users. Now, service account enable Kubernetes application or user application to communicate back to the OpenShift API. If we want to assign an application some permission to talk to the OpenShift API, we create service accounts and attach roles to it and assign it to the application. We also have groups, which is basically a collection of users. A role, which is also a local role. These roles are also known as local roles. Roles are basically assigned to user groups or service accounts to provide them permission. A role is a set of permission that enables user, group, or service account to perform API operation over one or more resource type. Then we also have cluster roles, which provide cluster level administration permissions to the user. Finally, we have role bindings. Role binding assign a single role to a user. For local roles, we have local role bindings, and for cluster roles, we have cluster role bindings. The OpenShift authentication is managed through an OpenShift authentication operator. which is an OAuth toolkit. We can also integrate and modify our custom resource to integrate with supported identity providers, such as we can integrate it with LDAP, we can integrate it with Red Hat Keystone. We can also create basic permissions. We can integrate it with GitHub and GitLab, and we can also now integrate it with Google. OpenShift implements a software-defined networking to manage the networking infrastructure of the cluster and the user application. Software-defined networking is a networking model that allows you to manage the networking services through the abstraction of several networking layers. This basically decouples the software that handles the traffic from the underlying mechanism. OpenShift creates a cluster network. This cluster network is established and managed by the OpenShift software-defined networking, which is configured over an overlay network using the Open vSwitch. Again, OpenShift networking and software-defined networking is deployed through a networking operator. So you don't have to manage or implement or even scale your networking infrastructure. The networking mode, there are basically 3 software-defined networking modes that are available to a project. We have the multi-tenant mode, which basically isolates projects and namespaces from each other. In this mode, a project will not be able to communicate to a different project. A pod in one project will not be able to communicate to a different project. Next, we have subnet mode. In subnet mode, we have a flat network, which means that all pods will be able to communicate all the other pods in a different project. Finally, we have the networking policy mode. This is, by the way, the default policy mode as well. This allows the project owner and the project creator to define its own networking mode. He can choose either subnet mode or multi-tenant mode. He can isolate his network or create a flat network. OpenShift now support Multus container network interfaces. The idea behind Multus container network interfaces is that it allows multiple networking interfaces to be attached to a single pod. With this, we can create network function virtualization, such as we can build routers and switches, and we can even build customized load balancers if we want. Multus is now fully supported with Red Hat OpenShift 4. We have already discussed services, but I wanted to go a little bit in detail about service types. We have basically 4 different cluster types, services types that are available. First, we have the cluster IP. Cluster IP is the default type. It exposes the service on the cluster internal IP. You can reach the service only from within the cluster. Next, we have the node port type. The node port type of a service exposes the service on each node port's IP at a static port. A cluster IP service is created automatically, and a node port service will be routed to it. In this case, the administrator will have to manage and keep a list of all the ports that are available on its nodes. Next, we have the load balancer type. The load balancer service type exposes the service externally using a load balancer of the cloud provider. The external load balancer routes the port back to the cluster IP, which is automatically created. External DNS type name maps the service of the IP to an external DNS name. OpenShift routers allows you to expose your application to external networks. With routers, you can access your application with a unique hostname that is publicly accessible. Routers rely on a router plugin to redirect the traffic from public IP to the pods. This direct access to the pod allow routers to be much more feature rich compared to the Kubernetes ingress. Routers have the ability to create sticky sessions. So for example, if your application cannot handle session and requires session handling, and it is not managing its own session centrally, then we can enable sticky session on the routes. Routes also provide secure connections, which means you can build TLS SSL certificates and keys so that your communication between the client is completely encrypted. Routes basically provide three different types of secure routes. We have the secure route for edge, in which the TLS and the SSL certificates are installed directly on the router, and the communication between the client and the router is completely encrypted, but the communication back to the pod is unencrypted. If we want to encrypt that back traffic as well, we can use something like re-encrypt, where not only the router has the TLS SSL certificates, but also the pod is also assigned those TLS SSL certificate. They could be different TLS SSL certificate, or they can use the same certificates. Finally, we have the pass-through type as well. In the pass-through type, the connection is passed through from the route directly to the pod, and the pod will have to handle the TLS SSL encryption. OpenShift Container Platform uses the Kubernetes persistent volume framework to allow cluster administrator to provision persistent volume and persistent storage for their clusters. Developers can use persistent volume claims to request persistent volume resources without having to know the underlying knowledge of the storage provider. Persistent volume resources on their own are not scoped to a single project. They are shared across the entire OpenShift cluster platform, entire OpenShift container platform, and can be claimed by any project. So there are two common API calls that is used. One is the persistent volume API, which is used by the administrator to create persistent volume. And then you have the persistent volume claim API, which is used by the developers to provision volumes for their pods. So for example, we'll have a storage administrator who will have pre-configured the storage volumes in the pool, in the persistence pool volume. The developer can create a persistent volume claim as part of the pod definition and claim that persistent volume. Now let's take a look at the life cycle of a volume. Initially, we'll have a persistent volume that is pre-configured by our storage or cluster administrator. A claim would be created and binded to a pod. Once that pod comes to life, it will claim that persistent volume, and then it will be protected. What that means is that no other pod will then be able to use that exact same persistent volume. Finally, at the end of the life of the pod, or the end of the life of the application, that persistent volume is released. And based on the policy of the life cycle that storage administrator has created, the persistent volume could either be recycled, could be completely destroyed, or the data could be retained. The first thing I want to show you is about doing an installation for Red Hat OpenShift. The installation is actually quite easy. You basically have to go to cloud.redhat.com/OpenShift. There you can get a free subscription of 60 days. As you can see, that I'm also using a 60-day trial. If you don't have an account, you can just easily create one. You can go to create cluster. You can choose the OpenShift container platform and choose your preferred container platform. There are a lot of supported platforms that are already available, and one that is missing is Hyper-V. Hyper-V will be supported by the end of this year, and I think with OpenShift 4.7, we'll have the Hyper-V also available here. In my case, the platform that I'm using is AWS. I'm going to choose the AWS platform, and then I have two options. I have the user provision infrastructure, and then I have the installer provision infrastructure. Now, in the user provision infrastructure, in the user provision infrastructure, you will create your own VPCs, your own infrastructure, your own network. But in the installer provision infrastructure, the installer will automatically create all of that. Once you choose to download the installer, you will also download a pull secret, and you will also download the OC client. The installer is basically a Terraform run command, and it will basically create the entire infrastructure that is needed to run the application. Finally, when the installer is running, it will ask you for a pull secret, and it will also ask you for a domain that is required and your access key to the AWS or whatever platform that you're using based on that. Now, I already have a cluster provision where I have 3 master and 3 worker node. I also have my workstation that is running on the AWS platform. I will just quickly connect to the cluster platform and show you a few tricks. I hope you guys can see. Can somebody verify that you guys can see?
Zoom
okay, I'll just
bit.
zoom it a little bit. Okay. So after I have completed the installation, I will get a installation configuration file. You can define any folder file. In my case, I defined the installer config file. Inside that, I'll have the TLS certificates. I also got an auth configuration file. If I just quickly cat that out, kube config. So this basically contains all the certificate and the configuration file. All I need to do is basically export that. I have quickly, this is just an export command that is exporting the OpenShift endpoint and the certificate so that my communication between the endpoint is completely encrypted. I just need to run that, and then basically I can do something like that. I can basically connect to it. I also have a password file which is available in the installer auth and kube admin. This kube admin is basically the default user. This password is automatically generated. You can use that to log in. I already have logged in using in my OpenShift container platform. But before we go to the GUI, we'll just have a quick look with the console. So I can basically run OC get pods and get a list of pods that are already running. I could run the OC get nodes and have a look at all the worker and master nodes that are running. The OC command is quite rich in the sense that you don't even need an SSH connection to your worker and master node. You can basically run the debug command, and you can specify any node that you want to connect to, and you will be able to connect to it. It will automatically create a backend connection to it, and I just need to run a chroot/host, and then I'll be directly logged into it. I can, for example, see the status of my container runtime engine, which is running perfectly fine. That's good. And I can also look at the kubelet agent. That is, I think the console is a bit slow. Can't do much about that. Kubelet agent, I can run kubelet agent and see that kubelet agent is also running.
Okay, go slow. It's taking time.
Finally, if I want to exit I will run Control D. I apologize. I think the session is coming quite slow on the monitor that I'm looking at. I'm not sure how you guys are getting it. So there's also projects. I can run the OC project command. Project command, and see what project I'm running. I'm already in. I'm in the default project. I can create a new project by running the OC new project, and let's name this OC demo. And this will this has already created a namespace, certain permissions for me, and now I can run the run my application inside it. I already have a GitHub repository, which I'll share with you guys just a moment. So basically, this is a GitHub repository, which is basically you can see that there is no Docker file or any build file. Normally, you require these build file to build the image or to perform a build command. This just contains an index.php, which runs the info.php command. Now, in order to run my new application, I just need to run OC new new app, and I need to tell that this is a PHP application, and I just quickly need to copy the URL of this repository. This is a public repository, that's why I don't have to provide any credentials. If this was a non-public repository, I'll have to provide credentials as well. So it's not going to prompt me for any credentials. So basically that's it. It's automatically going to, let me just run this pods command, and we'll notice how it is automatically building building our application. So right now the pod that is running currently is a build pod. It is downloading the source code repository. It's going to take a bit of a minute or so to basically download our repository, and based on the PHP command that I gave initially, it's going to understand that it requires the PHP runtime. Just let's give it a few minutes, and it will automatically go into the next state. Okay, so as we can see now, a deploy container was also deployed. With this deploy was responsible for running our pod. It is still running. The build will also die in a few minutes. Okay, no, sorry. The build and the deploy has terminated. They have completed its state, and now we have a running pod. So if I now quickly run a OC get pod, I will see that I have one container of my application running. The new app command has automatically created the pod definition for me. It has created the service definition for me. So if I run get svc, it will show me that the service that is automatically created, and notice that it has a cluster IP. It is the default type, so that's what has been defined. If I do a quick deployment config, we can see that the deployment config is also created. But this application at this point is not exposed to the internet. We need to expose that using, as you remember, we talked about routes. So I can run that by expose. I will define the deployment config that I want to expose. I will give the php.info. And okay, so that will basically create the route for me. I'm having some difficulty creating it, but let me just show you how to scale this application as well. So in order for me to scale the application, I will simply have to enter a scale command, and I will define the deployment config that is basically assigned. And I will say php info, and I will tell the replica to be, let's make the replica 10. replicas. And now if I do the get pods, we will see that a lot of more pods will be launching up. In a few minutes, in fact, it's already launched. All 10 pods are now launched. This is something that I have done manually. I could also automate this using the auto scaling, horizontal pod scaling command. I can run OC auto scale. I will again define the deployment config, which is php info. I will define the minimum. Let's say it's 10, and I will define the maximum to be 20. And I will select our CPU metric, which will be in my case CPU percentage, and keep that at 80%. So now the horizontal pod scaling has been auto scaling has been created, and now if our CPU load is increased, we will see that the application will be automatically scaled. Now let's go to the console. If you guys can see the console, okay, and we can go inside. This is basically I have logged in through the kube admin, which is the default admin user. The password I showed you was used to log in. We can go into pods and see that there are no pods running. I have to choose my current namespace, and as soon as I select the correct namespace, I can see my pods are running. It will also provide me a lot of metric if I go into any of these pods, a particular metric for that particular pod. I can go inside deployment config. This is the deployment config that was created, and the replica controller that it created was right here. I can even modify the whole thing that I did from there. Instead of doing from the CLI, I could do some of these administrative tasks from here. I can just say that I need 5 pods instead of 4, and we will notice that it is now it will automatically scale down to the 5 pods. I also want to show you those cluster operators. So if we go into administration and cluster setting, we can actually look into the cluster operators that are actually running our OpenShift container platform. And these are all the pre-built operators that are installed in our application, in our platform. Plus we have this operator tab. I could go into operator hub and basically install any of the operators that are available. So some of these you can see are community operators, and some of them are the Red Hat certified operators. For example, this ActiveMQ is being provided by Red Hat. So if I install this particular operator, we can see that the complexity of this operator is basically basic install. It does not go as far as autopilot. But let's choose something that can do that. This again has the complexity as far as seamless upgrade. So let's install that one. Now remember, when I install it, I'll have to subscribe it. And this operator is now installed in my particular project. It's not available into all the projects. There are certain operators, for example, authentication. It will be available in the authentication namespace and authentication project. So once this is basically installed, it will automatically take care about launching this Akka cluster, and we can utilize it. I think we are already ahead of time due to some issues with the connectivity. We will now move on for any questions. We are overboard, and I'll just stop my sharing my screen.
People also who have joined.
All right, I guess then that's it. Thank you everybody for attending this webinar. Hope you had a good time, and you learned something from this webinar. Anyway, thank you very much.
Thank you. And if you want to add anything, like if